This video is on diffraction and two-slit diffraction. Question 1. Define diffraction. Give 2 examples. Diffraction is the spreading of waves around an object. So one example is when sound waves spread or diffract, so people can hear others if they are in another room. Another example is when light waves spread or diffract through a small slit. When defining diffraction, do not use the word bend. Don't say diffraction is a bending of waves around an object. Question 2. What is the relationship between the slit width and wavelength of the wave which gives maximum diffraction? If the width of the slit is about the same length of the wavelength of the wave, then the diffraction will be maximum. So take a look at this image on the top left. The wavelength of this incoming wave is the distance between the 2 vertical lines. And that length is about the same as the opening of this slit. So you see the spreading of this wave once it passes the opening is maximum. Question 3. What is the relationship between the slit width and wavelength of the wave which gives minimum diffraction? If the width of the slit is much longer than the wavelength of the incoming wave, or if the width of the slit is much shorter than the wavelength of the incoming wave, then the diffraction of the incoming wave will be minimum. And obviously, if the width of the slit goes to 0, then no waves will come out of the other side. So take a look at this bottom left image. The wavelength of the wave, which is the distance between 2 crests, is much shorter than the slit width. The slit width is much longer, and because of that, there's not much diffraction. You see much more diffraction when the wavelength of the wave is equal to the opening of the slit. Much more diffraction on the top left than the top right. Question 4. Light passes through a slit which is equal to the light's wavelength. What happens to the intensity of the central maximum as the slit width decreases? Okay. So, as the width of the slit decreases, then the intensity of the central maximum will decrease since there will be less waves going past the slit. So, on the left side you see a laser. Then the laser emits light of a specific wavelength. That's where it says light waves emitted by the source. Then there's a single slit, screen with a single narrow slit. Then we get diffraction. You need to memorize this pattern on the very right. The central maximum is where we get constructive interference. You see this red part here. Then you see this black spot. That's called the destructive interference, or a minimum. Then you get another central maximum. Then you get destructive interference, then constructive interference. So all the red is constructive interference. All the black is destructive interference. So to answer the question, the length of the central maximum will decrease if the width of the slit decreases. Question 5. The equation for double slit wave interference is S equals lambda d over d. Define the following variables and draw a neat and detailed intensity versus displacement graph for double slit interference. So little s is the distance between maximum intensities, or bright spots. Lambda is the wavelength of the wave entering the double slit. Remember Roy G. Biv. Red, orange, yellow, green, blue, indigo, violet. Indigo violet means purple. Big D means distance from the double slit to screen. And little d means distance between two slits. So, important, the length of the slit opening is not in this equation. Okay. So, in two-slit interference, we have something that looks like this. We have two slits, and a wave comes up, and now we get constructive and destructive interference. So we get constructive, a maximum in the middle, then destructive, then constructive, then destructive, constructive, destructive, on and on. So this is what you should be drawing here. And this is another image. The central maximum gives us constructive interference. And then when we go a little bit to the right, we get a black spot, which is destructive, then a bright, then a black, then a bright, then a black, then a bright, black, bright. Okay. So the central maximum is n equals 0. And then the horizontal distance from one bright spot to the next is s equals 1. Then to the next one is s equals 2. And it keeps going. So it looks like this. N equals 0 is in the middle. N equals 1 is the next central, the next maximum. N equals 2 is the next maximum. By maximum, I mean constructive interference. So from n equals 0 to n equals 1 is s. From n equals 0 to n equals 2 is 2s. Okay. So this picture is not drawn to scale. Most of the action is near to the center of the screen. Most of the action is really, really down here. So if big D is large, then the two blue lines are nearly parallel to each other. Then these lines are nearly parallel to each other. The blue ones. So once again, n equals 0 is the central maximum or primary maxima. N equals 1 is the second primary maxima. N equals 2 is the third primary maxima. So this is another image. This is another image. Question 6. Play with the following simulations, draw and record what you learned. So with this simulation here, go to this website and then answer these questions. What happens to the distance between the two nodes when the wavelength increases? Node means a minimum, destructive interference. So you can play with the wavelength, distance between slits, slit width, and central maximum. Okay. What happens to the distance between the nodes when the distance between the slits increase? What happens to the distance between the nodes when the slit width increases? Okay. And finally, click on the Include Diffraction option. Vary the wavelength distance between slits and slit width. What do you observe about the antinodes and distance between the antinodes? Antinodes are locations of maximum. Okay. So go on this website also and play with the simulation. So click on the laser pointer on the left. What happens to the diffraction pattern as the color of laser light varies? Okay, so we could change the color of this laser light. Click on the slits. That's the middle image. What happens to the diffraction pattern as the distance between the slits increase? Finally, drag the screen to the very left where it says drag me. Okay. What happens to the diffraction pattern as the distance between the slits and the screen increases? So this black screen, you're going to drag it to the very left, and then you're going to move it to the right, and then you're going to see what happens to this pattern. Question 7. You are looking at a sodium discharge tube with lambda equals 5890 angstroms through a double slit, which has a distance of 0.170 millimeters between the centers of the two slits. The light source is placed 1.2 meters from the double slit. What will be the distance between the interference fringes visible on the screen? So, we were given lambda. We were given big D. And finally, we were given little d. So we could use those three values to solve for little s. Question 8. Monochromatic laser light, which has a wavelength of 555 nanometers, is shown on two slits which are 0.125 millimeters apart. Calculate the distance the fringes are from each other on a screen, which is placed 6.25 meters away from the double slit. So we were given everything to solve for little s, to determine little s. Finally, two slits are separated by 0.565 millimeters. So that's little d. And the screen is placed 2.25 meters from the two slits, so that's big D. The center of the first fringe and the center of the sixth fringe is separated by 8.75 centimeters. So see what I did here. Little s is going to be 8.75 times 10 to the minus 2 meters divided by 5. Calculate the wavelength of the monochromatic light. So we know the equation S equals lambda big D over little d. Solve for lambda, and we could find the value.